session on proof system. So the first talk will be about distributed proven interactive proof. And Rex is giving the talk.
Okay. Thanks for the introduction. So yeah, I'm Rex, and I'm going to be talking about how to achieve succinct interactive arguments with a distributed proof. And this is joint work with Sorel Daz, Ilan Komogodsky, Elaine Shi, and Brigitte. So let's start by quickly reviewing what the goal of an interactive argument is. So the setting is that we have two parties. We have the prover and the verifier. And so we assume that both the prover and the verifier have some statement X in common with respect to some NP language.
Closer to the microphone.
Can you hear me better now?
Yes.
Okay, cool. Yeah, so the setting is we have the prover and the verifier. We have a shared statement X, and then the prover has some witness W. And the idea is that we want some interaction between the prover and the verifier such that if the witness is a valid one, then the verifier should accept. And on the other hand, if the statement is false, if there's no witness, then the verifier should reject with high probability. So like I was saying, the setting that we're studying is succinct arguments. So you might think, okay, so why can't the prover just directly send the witness to the verifier? And this actually is a valid interactive argument, but you can consider a setting where maybe there's sort of a high unbalance in the power of the prover and the verifier. So maybe the prover has some powerful machine and the verifier has some cell phone or something, and those are the two machines that are performing the protocol. And you can also think about a setting where maybe the network has a high latency or the cost is large. And so, in these settings, maybe it's too costly to just send the witness in the clear. And so the idea is that we want an argument system where the transcript of the messages sent is much smaller than the witness size. Yeah, so this type of argument has had a long history of studies, starting with Killian in 1992, who constructed the first such argument system. So like I was saying before, our specific setting that we want to study is a setting where we have a distributed prover. So what I mean by that is, let's imagine that now, let's say that the witness is extremely large. Let's say that it's so large that it can't fit on the local storage of any one machine. You can imagine, like, let's say that Google wants to prove some statement about the entire search index, or OpenAI wants to prove something about the entire training set that was used for ChatGPT. So in this setting, the witness has to be broken up among many machines. And so we can ask the question, like, is it possible to construct an argument system that works in this setting where, the provers sort of, they work together and they also interact with the verifier in order to convince the verifier. And notice here that, in this setting, naturally the communication between the provers also has to be small. Because if you're a prover proving one of the proving machines and you can't store the entire witness, you obviously also can't store incoming messages that are proportional to the whole witness size. So before we move on, one question we might have is like, is this possible? And if it's possible, is it possible for all languages? What kind of languages can we support? So it's if we could construct a generic argument that worked for any NP language with a distributed prover where the communication is succinct, then that seems a bit fishy, right? Because that might contradict some complexity theory, or that might solve some complexity theoretic question related to parallelization of languages. So I'm just gonna in terms of this question of like what languages we can support, I'm just gonna sort of put that aside for a second. And we're just gonna, let's focus on sort of a simple case. Let's focus on a simple language, which works as follows. So let's imagine, like I said before, so the witness is going to be, split among all of the provers. So each prover has a piece of the witness. And we're going to work with statements which are essentially conjunctions, where each term in the conjunction can be checked locally by a single machine, a single proving machine. And so in this case, there's a particular very powerful, tool that we can use, a succinct non-interactive argument of knowledge, or a SNARK, that we can use in order to get, an argument system with a distributed prover. And let me just explain that quickly. So the idea is, once we have this SNARK, each prover can just non-interactively generate a succinct proof of their term in the conjunction. And just for the sake of argument, let's say that these are extremely succinct. Let's say that they're completely independent of the witness size. So now we have this. What we can do is, let's say that prover 2 sends its proof pi2 over to prover 1. So now prover 1 has proofs proving term 1 and 2 are true in the conjunction. And now what this prover can do is it can just apply the SNARK again. So it can create another proof where now the statement of the proof is, I saw a correct proof for term 1 and term 2. So the witnesses now are the original proofs, pi1 and pi2. And because of the succinctness property of a SNARK, this, the proof size doesn't move. It basically stays, you can think of it as staying constant. And so this technique is very powerful. It's called recursive composition. And you can imagine all of the provers sort of doing this sort of recursive composition procedure in sort of a tree-like fashion, where at the end, prover 1 has a single proof, a succinct proof that's independent of the witness size, independent of the number of parties, and that proves every term in the conjunction. So basically, it proves the entire statement. And then this prover can just send this, non-interactive proof to the verifier, and the verifier can verify it offline. So this, this is a valid argument system that's succinct and has a distributed prover. But the catch is that it turns out that in order to do this, recursive composition, you kind of need non-interactivity. You need a succinct non-interactive argument of knowledge, and the non-interactive part is crucial here. And unfortunately, it was actually shown that if you want to use a SNARK, if you want these non-interactive succinct arguments, you actually need to make these very strong non-falsifiable assumptions. And yeah, so it's an important question whether you can do this without making these non-falsifiable assumptions. Yeah, so I should say that this, this impossibility result, this sort of lower bound that says you need non-falsifiable assumptions for SNARKs, it was proved by Gentry and Wicks in 2015. Yeah, so this, this is the first problem. The second problem is what I was saying before. So, this is a proof system or an argument system for a very simple type of language. And the question is, what can we do that's more general than this? Okay, so first to answer, to sort of go into the second question a little bit more, what we're going to do is we're going to try to expand the set of languages that we can work with beyond conjunctions, but still in sort of a limited way that we don't, accidentally solve some complexity theoretic problem. So what we're going to do is we're going to imagine, or we're going to work with languages where we assume every language that we work with has a verification procedure that itself can be represented as some, distributed algorithm. So, again, every machine now has a piece of the witness, and they work together to verify the statement. But notice, like in this, in this case, there's no notion of security. It's all the machines are assumed to be honest. And so now with this type of language, our question can then be, if we have such a distributed verification algorithm, how, is it possible to basically compile that algorithm into a secure argument system with a distributed prover that is succinct? And crucially, can we do this only using falsifiable assumptions? And for the main result of our paper, we show that the answer is yes. So in particular, we give a compiler where you can prove security using standard falsifiable assumptions, namely, for instance, RSA. And it has sort of reasonable blow-up. So the round blow-up with respect to the original, insecure verification algorithm is polylogarithmic, and the space overhead is polynomial. Okay, so I'm just going to explain so I'm going to take the last couple of minutes just to, give you sort of a flavor of the techniques that we use. So at a high level, the approach that we're going to take is we're going to construct a polynomial interactive oracle proof, or an IOP. And so essentially an IOP works as follows. So, in this setting, in addition to the prover and the verifier, we also assume that there's some essentially trusted party. We'll call this the polynomial oracle. And what the polynomial oracle allows is it allows the prover to essentially commit to some polynomial, some polynomial f. And in this case, we'll assume that f is multilinear. And then during the interactive phase, this oracle will essentially allow the verifier to make trusted evaluation queries to this committed polynomial. So the verifier can send x and it'll get back f of x. Okay. And so the idea here is that once we have a protocol in this sort of polynomial IOP model, then we can instantiate this oracle with a polynomial commitment and we get a protocol in the standard model. And so I'll be a little bit more specific about our approach now. So we're actually going to build upon the previous work of Block et al. In 2021. And this previous work, what they were able to do is they were able to construct a succinct interactive argument where the prover is essentially a streaming prover. So you can imagine the prover, it's still a single machine. There's no distribution. And it still gets access to all of W, just not all at once. And so with that in mind, what this previous work does is it works with a streaming polynomial. So the idea is that the prover can stream evaluations of the polynomial in question until once you have enough evaluations, you have a well-defined polynomial. And then the next step, the interactive step, is essentially a sum check argument over this polynomial f. And you can think of f as sort of encoding the witness, or just encoding the entire computation that the verifier wants to verify. And so what this previous work, how they made it work is, first they observed that you can actually compute the sum check prover's messages only given streaming access to f. So that's part one. And then part two is that they implemented a streaming polynomial commitment that allows for this sort of streaming mode of commitment and for a streaming evaluation groups. So essentially, what our approach was we tried to take this approach and sort of modify it for our setting. So now we have a distributed prover. We have many proving machines. And so each machine is going to submit some subset of the evaluations of a polynomial to this oracle. And then the idea is once all of the machines have submitted their evaluations, then you have a well-defined polynomial. And then again, we're going to do a sum check argument. And if you know about sum checks, the verifier is going to perform its final check using the polynomial commitment. Okay, so this is our overall approach, and then I'll just tell you a few problems we had to solve. So the first problem is essentially how do we represent this distributed interactive verification as a multilinear polynomial? Because previous work, although it was a streaming work in the streaming setting, the verification algorithm is still a single machine. So problem two is how do we modify the polynomial commitment to allow for distributed commitment and evaluation? And the third is how do we get the provers to compute the sum check provers messages in a distributed way? And so for the solutions to these questions, I'll refer you to our paper. So that's all I had. Thank you.
We have time for a very quick question.
So you mentioned that the communication complexity between the provers cannot be large because they can only store, the storage size is small, right? But they need not store the full transcript, right? Like the communication can still be large, like the transcript can be very large, but it can be just the next message function is just dependent on the previous function. So the transcript can be like,
Yeah, so I guess that I think that was part of my talk that wasn't completely clear. So you don't like, it's true that if you have a protocol that takes like order W uh, rounds, where W is the witness size, then of course you can have communication between the provers uh, that's proportional to the witness size without having the storage problem. But then you have you have a protocol that takes like an extremely large amount of rounds, right? So you also want to optimize the rounds as well. So if you have like, essentially, if you have the space requirement and you have some sort of reasonable round requirement, then you can sort of reasonably allow for for large prover communication.
okay, thanks.
Let's thank the speaker again. So the next talk will be locally verifiable distributed SNARKs, and Eden is giving the talk.
No, I don't. Okay.
Yes. Hi, I'm Eden Aldemachuva, and I'm going to tell you about locally verifiable distributed SNARKs. This is joint work with Ilet Boyle, Ran Cohen, Tal Moran, and Rotem Oshman. So let's begin by defining SNARKs. A SNARK is a computationally sound proof system where a prover and a verifier share a common reference string. The prover sends a proof to the verifier, claiming some input X is in the language L. Now, this proof should be succinct. Typically, it's polylogarithmic in the input size, and it should be much easier to verify than it is to decide whether X is in the language or not. Now, the soundness of this scheme is computational, meaning it's hard to prove a false statement, to find an input X which is not in the language, and a proof pi that nonetheless makes the verifier accept. Now, in this work, we're constructing SNARKs for distributed computations, and our distributed computing model is of a communication network where each node has its own input. And in a distributed algorithm, nodes exchange messages over the network's edges for some number of communication rounds. We think about polynomial number of rounds in the input size. Eventually, each node obtains its own output, and we define the language of a distributed algorithm A to be all triplets of a graph G, input assignment X and output Y, such that A on G and X outputs Y. Now, our SNARK is going to prove membership in these type of languages to the network nodes themselves. And we want that even if the original algorithm takes many rounds, the verification process is going to take few rounds. So a prover runs alongside the distributed algorithm, and it outputs in each node a certificate alongside the original output of the algorithm. These certificates, we want them to be succinct, and we consider succinctness as polylogarithmic in N, where N here is the combined size of the network itself and the inputs to the nodes. So in verification, nodes are going to receive these certificates alongside the inputs and outputs, and then they are going to perform only few number of communication rounds, and each node decides whether it accepts or rejects. We consider the network inputs, outputs, and certificates accepted if and only if all nodes accept. We call this a locally verifiable distributed SNARK, or LVD SNARK for short. It's a computationally sound proof system for distributed computations where the certificates to the node are succinct. The verification process is a local algorithm, meaning it takes only a few rounds using short messages. And of course, the usual completeness requirement holds as well. Now, this notion relates to both distributed proofs, which is a notion that we have in distributed computing. And this is actually the first computationally sound version of it, where we get more efficient solutions than in the current version. And it also relates to the SNARKs from standard assumptions world, where this fits quite nicely in the big picture of what we know to do from standard assumptions and what we don't know to do from standard assumptions. So there are two approaches for constructing these LVD SNARKs. The first one is a global prover. So here, the prover is going to be a centralized algorithm that sees a global view of the entire network and the inputs, and it just assigns certificates to the nodes. Now, as you're about to see, this yields a pretty simple construction. The only problem is that the ones that need to do the proving are the nodes of the network themselves. And in order for them to do that with a global prover, they first need to gather the entire information of the network in one place and then perform the computation. Now, this is very expensive in communication. So the other approach is of a distributed prover. Here, the prover is a truly distributed algorithm that just outputs the certificates in the nodes. And this yields a much more efficient solution, as nodes do not need in no point to collect the entire information in one place. But it takes much more effort in the construction itself and in its proof of soundness. Sorry. So in our work, after defining LVD SNARKs, we show two constructions for them. The first one with the global prover, where the main tools that we use are hash trees or hash families with local openings, and RAM SNARKs. And another construction for distributed prover, where we first define and construct a new object that we call distributed Merkle tree. And our second main tool is batch arguments for N. It's important to mention that in both constructions, they are from the CRS model, they are from standard assumptions, they have adaptive soundness notion, and the verification is not only local, but takes only one round of communication. So now I'm going to shortly show you our first construction of a global prover. Here, the first thing the prover does is take the entire representation of the network and inputs. Here it's the adjacency matrix, inputs, outputs of the algorithm, and it hashes them using a hash family with local openings. Now, the key observation here is that there are two things we can do with such a hash value. First, we can, for each node, open this hash to that node's information. And if we do that for all nodes, together this proves that this hash value is of the current network. And the second thing we can do is prove in a way that that hash value is of an instance of LA, the language of the algorithm. Now, when I say prove in a way, I mean RAM SNARKs, and this is a kind of a subtle notion. I'm not getting into this, but this has an asterisk on it. So without any more details, I'm going to go to our next construction of a distributed prover. Now here, I'm not going to be able to show you exactly what it does. What I am going to show you is a main challenge that is with constructing distributed provers and kind of an idea of how we face this challenge. So for the example, let's consider an algorithm that helps a group plan a party. In this algorithm, one node is the host and the rest are participants. And each participant inputs what they would like to bring to the party. And in this example, all participants would like to bring bamboo shoots. The participants tell the host what they'd like to bring, and the host decides what each participant will bring according to the following process. So if it's a new request, it says okay and insert it to a list. And if the request is already in the list, it tells the participant to bring beer instead. So here is going to reply okay for the left one and beer for the right one. And eventually each participant outputs what they're going to bring to the party. Okay. Now we want to prove to this network. Now this network woke up, the left participant has its output, the right participant has its output, and we would like to prove to them that this is the correct output of the algorithm. One way to do that, one naive way to do that, is using the transcript of the algorithm. Now nodes could verify two things. They can first verify that the transcript makes sense, which means they would actually send these messages. And given that this is their transcript, they would actually output this output. And the second thing they could verify is that these transcripts are consistent with each other over the edges. Now, this idea actually works. And in the distributed computing setting where we usually talk about perfect soundness, this, for some problems, is the best we can do. But for us, this is too long. So the length of the transcript depends on number of rounds, message size, and degree of the node. And each one of these things could be large. So to make things shorter, one might say, let's hash the transcript at each node. Now we have a hash at each node, and this is succinct enough. And let's assume, for the matter of the example, that we could easily have a proof at each node that this transcript that it has hash is a valid transcript that actually yields its output. And we ask, are we done? Is this enough? So to see why that's not enough, let's consider an adversary that tries to prove to both participants that they're going to bring bamboo shoots to the party. Now, this adversary is going to give the left participant and the host exactly the same hash values in proof it gave them in the honest case. And to the right participant is going to give the same hash value in proofs it gives the left participant. In this case, everyone are going to accept a false state. Now, this is a false state because in the original algorithm, there's no way both would bring bamboo shoots. And as some of you can see already, the problem is that underneath the hash value, we have unmatching transcripts. And because this is one hash value per node, we cannot check consistency between these values underneath the hash. So this was succinct enough, but not sound because we couldn't check consistency. So what if we hash a different hash value for each neighbor? Now the host has two separate hash values, one for each participant, and now this does work. They can check consistency, and this actually is sound. Now our problem is that it requires each node to have separate value as part of the certificate for each neighbor. And while in this example, it doesn't seem so bad, in general networks, we could have something that looks like that. And once we have high degree nodes, we cannot afford the certificate to grow linearly with the degree. So it seems that what we need is to have one hash value and to perform many consistency checks over it without having separate values for each such check. So our solution for this is our distributed Merkle tree. And before we go there, let's look at the outgoing messages at this example algorithm. And if we put all these messages together, we get the entire transcript of the entire network in the algorithm. If we hash these together, we get one hash value that is of the entire transcript of all the participants. And if we could magically have this hash value for all the nodes, our problem is solved. Because now we can prove to each node a proof that refers to that hash value. And we can also check consistency because nodes have the same hash. So this solves all of our problems. Now, how do we get this hash in each node? So that is our distributed Merkle tree. Now we go for a different network just to show what this Merkle tree is. So it's a Merkle tree of content that lies in the nodes. And each node has some fraction of a Merkle tree and an opening path to that fraction. And what's special here is that when these fractions are put together, they form the exactly same Merkle tree as would be constructed by an authority that sees the entire input. And now we want to achieve these fractions in the nodes without having to first collect the entire information in one place, compute the Merkle tree, and then spread the fractions. And our secondary result in this work is that we managed to do that in only O of D rounds, where D is the diameter of the network. And in each round, we only use polylogarithmic messages. And this actually solves our one hash many consistency checks problem. So to sum up, we define and construct locally verifiable distributed SNARKs. These are computationally sound proof systems for distributed computations, which give more efficient results than what we currently have. We construct both global prover LVD SNARK and a distributed one, and we use a new notion that we define of distributed Merkle trees. Thank you.
We have time for questions. So I do have one question. In the complete, so you define that is adaptive sound. Do you mean adaptive after you choose the CRS? The
Yes.
theorem is adaptive.
Yes.
Okay, but okay, thank you.
Yeah, so everyone shared the same CRS. So all of the nodes see it and the prover sees it. And then after the malicious prover would choose the network and the inputs after seeing the CRS.
Okay, thank you. So let's thank the speaker again. So the next talk will be online, and the title of the talk is "Your Reputation is Safe with Me: Framing Free Distributed Zero Knowledge Proof." And More will give the talk.
Yes, thank you. So this is joint work with Karmit Khazai and Muthu Venkita Subramaniam. So I'm going to talk about distributed zero knowledge proofs, and this is a non-standard setting for zero knowledge. So let me just start by defining the model. So in this distributed model, we have one prover and multiple verifiers. Everyone can talk to everyone. And the goal is to prove some NP statement. For example, that a graph is 3-colorable. So here the prover knows the graph and the coloring, but the verifiers might not even know the entire graph. It might be the case that each verifier only has some local view. For example, just knows the local neighborhood of one node. And zero knowledge in this context means that a subset of corrupted verifiers don't learn anything about the coloring, obviously, but also they don't learn anything about the rest of the graph. And framing free in this context means that a subset of corrupted verifiers can't frame the prover. So they can't cause the honest verifiers to reject a true claim. So as I said, this is a non-standard setting for zero knowledge, and you might ask yourselves, why do we even care about it? So the reason is that there are indeed many situations where we have one prover and multiple verifiers, and each verifier only has a local view of the statement. So for example, think of trying to prove honest behavior in MPC protocols. So if Snoopy wants to prove that he behaved honestly, the claim he's making is that the messages he sent are consistent with the messages that he received and with his input and his randomness. And this is an NP statement in which the witness is the input and randomness of Snoopy, and the statement are the messages that Snoopy received, and this statement is distributed between the rest of the parties. So this is one example. There are many other situations where DZK proofs naturally arise, and framing is a real concern in these situations. Another aspect of these types of applications is that you can actually divide the proof into two phases, a proving phase and a verification phase. Going back to the example of proving honest behavior, while you're executing the MPC protocol, and this might take several rounds, you can additionally compute some other information on the side, which is going to be used as the proof later on. But then once the MPC execution is done, you want to be able to verify the proof very efficiently. And what do I mean by very efficiently? I mean that the communication complexity during this verification phase should scale polynomially with the number of verifiers, but only polylogarithmically with the size of the instance, which is the communication of the MPC in this example. And our goal today is to construct distributed zero-knowledge proofs that are both verification efficient and framing free. So what do we know about these proofs? There have been many different works in many different models, as well as on related notions like verifiable relation sharing. The model we're working with was introduced by Bonnet et al. And in this model, the input statement is distributed between the verifiers. Soundness should hold against a prover colluding with verifiers, and we want information theoretic security. And the only difference between the Bonnet et al. Model and our model is that Bonnet et al. Don't consider framing, and we add the framing-free guarantee to the model. So in these different models, there have been different constructions. The most relevant for us is a construction of Bonnet et al., which give verification efficient DZKs for NP, but the prover can be framed in their construction. And actually, all of these constructions fall short of getting both verification efficiency and framing free in our model. So before I continue, I just want to note that we could have just solved the DZK problem by using generic off-the-shelf MPC protocols, but this would not give us verification efficiency. So to get something verification efficient, we really need to tailor something, tailor the protocol to the distributed zero-knowledge setting. So today I want to show you a framing-free, verification-efficient, distributed zero-knowledge proof for NP. We can handle 1/6 corruption, more or less. And actually, if you forgo the framing-free guarantee, then we can scale up the corruption threshold to roughly 1/2, and this matches the DZKs of Bonnet et al., which I mentioned in the previous slide. We get our DZKs using a new analysis for MPC in the head in the distributed setting. And this analysis is very different from a different analysis of MPC in the head in the distributed setting, which was given by Appelbaum et al. To construct VRS. And our construction also departs from the Bonnet et al. Construction, which was based on fully linear IOPs. We then instantiate this general approach using different MPC protocols to get DZKs that are verification efficient and have different trade-offs between the round complexity and the total proof length. And here we're using the flexibility of the MPC in the head paradigm, which is that we can instantiate it with different MPC protocols to get different types of results. And finally, we use our DZKs for several applications where the framing-free guarantee is essential to get the required properties of the application. So in the time I have left, I want to give you an idea of our DZK construction. And as I already mentioned, we could have just executed an MPC protocol between the prover and verifiers, but this would not have been communication efficient. But since the prover has a full view, she knows the input and she knows the witness, the prover could have actually executed the MPC on behalf of the verifiers. So executed the entire MPC in her head. And once the execution ends, the prover has a trace of the execution, which consists of all the parties' view in this interaction. And we know from the original MPC in the head paper, Avishai, Kushilevitz, Ostrovsky, and Sahai, that to get soundness, we just need to make sure that this execution was done correctly. And to check this, it's enough to check pairwise consistency between every pair of views. So checking that the messages reported in these views really do line up. So this already gives us a template of how to design distributed zero-knowledge proofs. And the idea is for the prover to execute the MPC in her head on behalf of the verifiers, and then send each verifier his view in this interaction. And now the verifiers just need to check pairwise consistency. So every verifier will locally check that his view is correct, and each pair of verifiers will exchange the messages and check that there is pairwise consistency. If some verifier notices an inconsistency, he'll complain, and if someone complains, we reject. So this is awesome, except that we're not getting verification efficiency. We're actually resending the entire communication of the MPC protocol, and we seem to have not made any progress at all. But actually, we have made progress, and the reason is that we don't need to resend the entire communication. All we need to do is check that the messages are identical. And to do this, we don't need to exchange the messages. It's enough to compute short information theoretic tags, max, on these messages and then just exchange the tags. And it turns out that we can generate all of the tags by just using one random field element. So now the idea is for the verifiers to jointly sample this random field element, toss a coin. Each verifier will locally compute the MAC, and each pair of verifiers will exchange the MACs between them, and then inconsistencies are determined according to these tags. And this already gives us a DZK that's verification efficient and matches the DZKs of Bonnet et al. But it doesn't prevent framing, because a verifier can always complain that he detected some inconsistency, and there's no way of kind of resolving this dispute of who's lying. Is it the verifier or the prover? And the idea to prevent framing is that we're going to eliminate all of the point-to-point communication. So everything is going to be sent over broadcasts. So now each verifier is going to broadcast all the tags. And then each verifier locally counts how, and then once you broadcast these tags, the prover can complain against verifiers that are lying. And now each verifier can locally count how many complaints there are. How many verifiers complained against the prover? How many verifiers did the prover complain against? And if there are too many complaints, the prover must be cheating. But if there are few complaints, we can attribute them to cheating verifiers and accept the claim. So we've prevented framing, but we've also possibly eliminated zero knowledge, because these tags don't necessarily hide the messages. So to get zero knowledge again, the idea is to one-time pad encrypt these tags. Each pair of verifiers is going to have a unique random mask joined between them and use this mask to one-time pad encrypt the tag. And it turns out that the prover can actually choose these masks, and that doesn't violate soundness. And the reason is that the prover chooses the masks before the verifiers toss the coin that determines the tags. So let me give you a very high-level sketch of our DZK proofs. The prover is going to emulate in her head an execution of the MPC protocol between all the verifiers. So executing the MPC on behalf of the verifiers. She then sends each verifier his view in this interaction, as well as the random masks you need to one-time pad encrypt the tags. Then the verifiers toss a coin. Each verifier uses this to generate the MACs and the tags, one-time pad encrypt them, and broadcast everything. Then there's a round of complaints, and each verifier counts how many complaints there are and decides whether to accept or to reject. So to sum up our construction, I just want to compare the MPC and the head technique in our distributed setting and in the two-party setting. So in our distributed setting, the prover executes the MPC on behalf of the verifiers. So the MPC parties correspond to verifiers. Then the verifiers compare all of the messages. So the entire execution trace is checked, and therefore the soundness error is independent of the number of parties in the MPC in the head. But the MPC in the head was actually introduced in the two-party setting in a seminal work of Yishai Kushilevitz, Ostrovsky, and Sahai. And in this setting, we only have one verifier. So the execution of the MPC in the head is over virtual parties. Each party holds a witness, secret share of the witness. And the number of parties determines the soundness error. Then the prover commits to the views in this interaction, and the verifier asks to check some subset of these views. So only a partial execution trace is checked. So let me summarize. I show you today distributed zero-knowledge proofs for NP that are both verification efficient and framing free. There's a lot more in the paper that I didn't have time to talk about, like instantiations and applications for which the framing free property is really essential. Thank you.
Questions? So I do have a question. So your threshold is 1.6, right? For the framing free. Do you think that is if you remove framing free is one half? Do you think that there is a lower bound that is different from 1/2 in case of framing free, or like is the lower bound different?
That's a good question. I wish I had a better answer than saying that I don't know. We've thought about this a little bit. So there's a work of GIKR from 2002 that construct VRS, which is very closely related to DZK. And they get information theoretic security like we do, and they also get 1/6 corruptions. So we're kind of matching their threshold, but we don't know whether we could improve it. In the computational setting, you can get close to 1/2, and this is by recent works by Appelbaum et al. I don't know why we get once. I mean, I understand why we get it in the proof, but I don't know whether there's a lower bound. No.
Okay, thanks. So let's thank the speaker again. So next talk is Beyond MPC in the End, black box construction of short zero knowledge proof. And Maur is giving the talk. So Maur, the stage is yours.
Thank you. So this is also joint work with Kalmit Chazai and Muthu Venkita Subramaniam. So this talk has two parts to it. In the first part, I'm going to show you a new paradigm for designing zero-knowledge proofs. And this extends the MPC and the head technique of Yishai Kushilevitz, Ostrovsky, and Sahai that I just talked about a couple of minutes ago. So our new approach replaces the MPC protocol with weaker primitives like fully homomorphic encryption, functional encryption, function or homomorphic secret sharing, randomized encodings, or laconic function evaluation, or even with interactive protocols like interactive proofs and interactive oracle proofs. And actually, you can use this paradigm not only to get zero-knowledge proofs, but also to get commit and prove functionalities. Then in the second part of the talk, I'm going to use this paradigm to show you new constructions of short zero-knowledge proofs. But this is really going to be towards the end of the talk. And if you're very curious to know what we get, I promise you in the end, there's going to be a scary table. So as I said, I'm going to talk about zero-knowledge proofs just in a few words, because I assume we all know what zero-knowledge proofs are. I'm talking about the two-party setting in this talk and interactive proofs. And our goal is to go beyond MPC in the head. So a good starting point is to know what MPC in the head is. So this is a really beautiful paradigm introduced by Yishai Kushilevitz, Ostrovsky, and Sahai in 2007 to construct two-party zero-knowledge proofs from MPC protocols. And throughout the talk, the NP relation I'm going to think of is proving that a circuit is satisfiable. So this is the high-level idea of the the paradigm, the prover emulates an MPC execution in her head, and the verifier checks that this MPC was executed correctly. For the purpose of this talk, you just need to know 3 ingredients of this technique. So the first is that the prover secret shares the witness in her head using an additive sharing. The second ingredient is that the prover uses an MPC protocol to somehow evaluate the circuit over the witness. So the prover runs an MPC protocol for a public function which reconstructs the witness from the secret shares and then evaluates the circuit. The prover then commits to the trace of this execution, which is the views of all the parties, and the verifier checks the correctness of the execution, but by opening up a subset of the views. The third component is how ICOs use the properties of the MPC protocol to get the properties of the zero-knowledge proof. And more specifically, they use the privacy of the MPC to prove zero knowledge, and they use the correctness of the MPC to prove soundness. So what they show is that all you need to do is to check that the protocol was executed correctly, because the correctness of the MPC guarantees that if everything was executed correctly, the outcome is the outcome of the circuit on some input, and this can only be 1 if the circuit is satisfiable. So again, 3 main ingredients to the MPC in the head technique: secret sharing the witness, evaluating the relation on the secret shares, and then using the correctness and privacy of the MPC protocol. You don't need fully secure protocols, just correctness and privacy. And this paradigm has been super influential, used in many applications beyond zero-knowledge proofs. I really don't have room in my slide to cite all the works on MPC in the head. But all these works, when they come to instantiate the MPC protocol, they use fully secure protocols and don't take advantage of this feature of MPC in the head, which is that you don't need full security. So today, the goal is to go beyond MPC in the head and base the paradigm on game-based primitives that allow us to encrypt secrets and homomorphically compute over them. So if I tell you I want a primitive that allows you to encrypt secrets and homomorphically compute over them, you should be thinking of fully homomorphic encryption, right? And indeed, this is one of the primitives that we use in our paradigm. And before I describe the general paradigm, I want to give an example of how to construct zero-knowledge proofs from FHE. And when I say FHE, I mean the public key primitive that has 4 algorithms: key generation, encryption, evaluating over encrypted secrets, and then decryption. So this is how we generate the proof. The prover first secret shares the witness in her head. We only need to share into 2 witness shares. Now the idea is to somehow use the algorithms of the FHE to evaluate the circuit over the witness. So the first thing the prover does is runs the key generation algorithm in her head to set up the scheme. She then encrypts the first witness share. She then evaluates, uses the evaluation algorithm to evaluate the circuit over the witness share, over the witness. And this is how we do it. So we define a new circuit C tilde, which is a private circuit that has W2, the second witness share, hardwired into it. This C tilde takes its input, XORs it with a hardwired W2, and then applies the original circuit C. And we evaluate this C tilde over an encryption of W1. So the outcome Y here should encrypt the output of the circuit C on the witness, which would be 1. Now the prover has a trace of the execution, which consists of the inputs and random inputs of all the algorithms and the outputs of all the algorithms, and this is what she sends over to the verifier. And now the verifier just wants to check that everything was executed correctly, and he's going to choose one of the phases of this execution and check that it was executed correctly. So for example, if you want to check key generation, you'll read the random input and the outputs and check that everything's okay. If you choose to check witness encryption, you will read the first witness share, W1. If you choose to check evaluation, you'll read the second witness share, W2, and an encryption of the first witness share, W1. But that's fine. because the encryption of W1 should hide this secret share. So you're basically only seeing one secret share. And then the verifier can also choose to check that the output does indeed decrypt to 1. So this gives us a zero-knowledge proof from fully homomorphic encryption, but actually it naturally generalizes to other primitives as well, where the idea is to replace the MPC protocol with a primitive that lets us encrypt over secrets and homomorphically compute over them. And then the proof is generated by secret sharing the witness, running the key generation algorithm, encrypting W1, the first witness share, evaluating over this encryption, where we evaluate a function, a private function that depends on W2, the second witness share, and finally decrypting or reconstructing the output from the outcome of evaluation. And we need 3 properties from this primitive. So we need correctness. This gives us the soundness of the zero-knowledge proof. And we need 2 types of privacy. The first type is input privacy. We need this because we evaluate a function that depends on W2 with an encryption of W1. So we need this encryption to hide W1. In some cases, we also need function privacy because when we check the output here, it was computed using a function that depends on W2. So we need the outcome of homomorphic evaluation to hide the function that was evaluated. So I showed you an example for a one-party primitive where we have one evaluator. You could have used other one-party primitives like functional encryption, laconic function evaluation, or randomized encodings. The paradigm can also use multi-party primitives like homomorphic or function secret sharing, where we have multiple evaluators. You could actually have also used interactive proofs or interactive oracle proofs, or both secret key and public key primitives can be used in our paradigm, and also primitives with imperfect correctness. So really everything goes. And actually the same paradigm also extends to giving not just zero-knowledge proofs, but also commit and prove style functionalities. So this paradigm is very versatile, and we exploit this versatility to get different zero-knowledge proof constructions based on different instantiations of these primitives. So at a very high level, we construct zero-knowledge proofs that are constant round and have constant soundness error, and use the underlying primitive as a black box. And this is what we get. So I promised you there will be a scary table. So let me just highlight a few of our results. The first result is a construction of zero-knowledge proofs for NC1 with communication that approaches the witness length based on the DCR assumption. Or more generally, this construction uses homomorphic secret sharing in a black box way, but to get the communication that we want, we instantiate HSS based on DCR. So before our work, the original Ishai, Kushilevich, Ostrovsky, and Sahai paper from 2007 gave a zero-knowledge proof with the same communication for AC0 using one-way functions in a black box way. So you can think of our result as a scaling up of the ICOS result, showing that you can scale up AC0 to NC1 by scaling up the assumption from one-way functions to DCR. Then we have another result for NC1 with the same communication using one-way functions as a black box, where the previous results use the one-way function in a non-black box way. And then I think that looking at these two results, it seems a bit confusing because the second result seems to subsume the first one, but actually these results are incomparable. And the reason is that this second result here from one-way functions, while we do have constant rounds in the zero-knowledge proof, the exact round complexity depends on the relation that we're proving. Whereas in the first result, based on DCR, the round complexity is bounded by a constant, a universal constant that's independent of the relation. And then we have a bunch of other results for other complexity classes where we give black box alternatives to existing zero-knowledge proofs with the same parameters, but that used the underlying primitive in a non-black box way. And I just want to make two comments about the statement I just made. The first is that we don't improve over the Chazai and Kita Subramanian result here. They were also black box in the one-way functions. But what we do is we show that we can get their result as a special case of our paradigm. And the second comment is that we give a black box alternative to a recent zero-knowledge proof of Nassar and Rothblum here. And we do pay a little bit for the black box because we get a constant here, which is slightly over 2, and they can go down very close to 1. So in summary, I showed you a new a new paradigm to constructing zero-knowledge proof based on game-based primitives. It's a very versatile paradigm. We tried several primitives. We didn't try everything out there. So I encourage you to take your favorite primitive and try to cast it into our paradigm and see whether it works. And we exploited this versatility to give zero-knowledge proofs with either new parameters or black box alternatives to existing results. Thank you.
Questions?
The FHE-based thing, as far as I can tell, doesn't use compactness. So you can do YAO-based, for example, to use with that construction. Right? I mean, there's no reason why the ciphertext needs to stay small. It can grow with the computation, so your communication grows a little bit, but the construction stays the same, I think.
We could have used garbled circuits. Is that what you're saying?
For example, yes.
So this is when I say randomized encodings here, so garbled circuits is a special case. And we do, to get the Chazai and Kita Subramanian result, we use garbled circuits, yes.
Thanks.
Yes. Cool. Yeah, I was wondering whether if you go back to the table, you said that the second construction based on DCR, the first line based on DCR does not, the communication complexity does not depend on the depth of the computation, but something probably does, because otherwise it would just work for NP, right? Like what depends on the depth of the computation?
The size of the computation.
It only depends on the size of the computation? Nothing like the
So,
security? Like what if the depth was more than polylogarithmic?
So you need to, the question is, how do you get the results, right? So this HSS, we only know how to get it with the communication that we want for NC1. This is...
Okay.
Do you understand what I'm saying? So you improve HSS. If you give me a better HSS, you give me a great HSS for NP, I give you a great zero-knowledge proof for NP, but I'm restricted by what the primitives, I mean the instantiations of the primitives that we currently have.
Okay, so the limit is in the HSS. Okay, thank you.
Okay, let's thank the speaker again. So the next talk is rough instances security for batch knowledge proof, and Amit is giving the talk.
Just a second. So this is the screen, right?
Yeah.
Okay. So hello, everyone. My name is Amit Sharabi. This talk is about rogue instance security for batch knowledge proofs. This is joint work with Gil Segev and Eilon Yogev. So one of the simplest proofs of knowledge is Sigma protocol, which is a 3-round protocol where the prover wishes to convince the verifier it knows a witness W, such that X and W are in relation R. We require the trivial completeness and another 2 properties. The first one is special soundness, which means that given an instance X and 2 accepting transcripts with a common first message alpha and distinct challenges beta, one can extract the corresponding witness. And the second one is zero knowledge, which means that the verifier cannot learn any additional information from the interaction with the prover. For the security of the protocol, we consider a hard distribution D, which means that given an instance sample from D, it's hard to extract a witness. And we say that the protocol is T epsilon sound with respect to hard distribution if for any T-time adversary, the probability that the verifier is going to accept given that the instance witness pair was sampled from the hard distribution, is bounded by epsilon. Using the forking lemma, for example, the assumption that the distribution is hard and the special soundness property of sigma protocols lead to T epsilon soundness with respect to hard distribution. One of the most influential sigma protocols is Schnorr protocol, which is a proof of knowledge for the discrete logarithm problem. Both the prover and the verifier holds an instance g to the w, and the prover wishes to convince the verifier it knows w. The protocol is as follows. The prover samples some random r and sends to the verifier g to dr. The verifier samples some challenge e, and the prover responds with r plus e times w. The verifier accepts if and only if g to the gamma equals to alpha times x to the beta. The security for Schnorr protocol is usually proven by a reduction to the discrete logarithm problem. Shoup showed that every t-query algorithm solves discrete log with probability at most t squared over p, while the best-known security bound for Schnorr protocol is recently shown by Rotem and Segev and bounded by t squared over p to the power of 2/3. In order to derive this bound, they used a new assumption that they call the second moment assumption, and we will define it later on in this talk. So now that we have a proof of knowledge for a single instance, but now what if we wish to convince knowledge for multiple instances? So now both the prover and the verifier holds k instances x1 to xk, and the prover wishes to convince the verifier it knows all corresponding witnesses. The first trivial solution is to invoke the original protocol on each one of the instances separately, which can be done in parallel. However, this leads to a factor of k in the communication complexity of the protocol. So our first question is how to batch sigma protocols while preserving small communication. And secondly, even if we have more efficient protocol, we ask what soundness notion should apply for batch knowledge proofs. Since in the single instance case, the soundness notion was trivial. We only had one instance. But now when we have k instances, some of them may be honestly generated by a hard distribution D and some of them may not. So in order to answer this question, we give a new notion of knowledge soundness, which we call the ROG instance soundness. And this is a very strong soundness notion and inspired by the ROG key security for multi-signature schemes. This notion considers a hard distribution D and the settings in which the malicious prover is provided with an honestly generated instance x1, which is sampled from a hard distribution, and then may choose the rest of the batch instances adaptively based on x1 in order to convince the verifier it knows all corresponding witnesses without actually having the knowledge of the witness w1. That is, the prover is provided with an instance x1, which is sampled from a hard distribution D, and then chooses the rest of the batch instances adaptively based on x1. We capture this in a simple game, which is to sample the instance witness pair from a hard distribution, then to invoke the malicious prover on the instance x1 in order to get the rest of the batch instances x2 to xk, and then we continue to follow the original sigma protocol. We sample some challenge beta, the prover responds with an answer gamma, and the verifier decides whether to accept or reject. So now that we have a notion of knowledge soundness for batch protocol, it is left to see whether can we batch sigma protocols while preserving small communication. Our main theorem says that every algebraic sigma protocol for one instance, which we will define the notion of algebraic sigma protocols later on in this talk, can be transformed into a batch sigma protocol for k instances with the same communication C while preserving zero knowledge. Then we assume that the distribution is second moment hard and derive a ROG soundness bound for our batch protocol, which is bounded by t squared over the size of the witness space to the power of 2/3. Using our theorem, we derive batch Schnorr protocol with ROG soundness, which is bounded by t squared over p to the power of 2/3. It is in fact matches the state of the art of Rotem and Segev for a single instance Schnorr protocol and does not depend on k at all. In fact, the batch Schnorr protocol was already constructed, however, the security bound relies exponentially in k. Practically, if we set the group size to 2 to the 256, the attacker's running time to 2 to the 80, and the number of batch instances k to 6, the previously known bound to Schnorr protocol is only 2 to the minus 14, while our algebraic bound is 2 to the minus 64. But what I didn't tell you about is the assumption that we used in order to derive such bound. We said that the distribution is hard if given an instance sampled from a distribution, it's hard to extract the corresponding witness. Here, instead of considering the hardness with respect to strict time algorithms, we consider the hardness of extracting a witness with respect to expected running time algorithms. The second moment assumption was recently introduced by Rotem and Segev and considered the second moment of the expected running time of the algorithm. Formally, we say that the distribution is second moment hard if for every algorithm A, the probability it succeeds in extracting a witness is bounded by the second moment of its expected running time over the size of the witness space, where now TA is a random variable instead of a strict parameter. In order to give evidence to support the hardness of the second moment assumption, we showed that it holds for discrete log in the generic group model. So, just a quick reminder, we give a new notion of knowledge soundness, which we call the ROG instance soundness, and showed how to batch sigma protocols that satisfies this notion. So for the technical section, we start by showing our batch protocol. But first, we need to define the notion of algebraic sigma protocols. A sigma protocol is algebraic if there exists an homomorphic one-way function f over two abelian cyclic groups such that the prover wishes to convince the verifier it knows the pre-image of f on W. The structure of such protocol is as follows. The prover samples some random R and sends to the verifier f on R. The verifier samples some challenge beta and the prover responds with R plus beta times W. The verifier accepts if and only if f on gamma equals to alpha times x to the beta. This may seem to be very familiar, since Schnorr protocol is an algebraic sigma protocol, where the function f on x equals to g to the x. So now that we have the notion of algebraic sigma protocols, we are ready to show how to batch them into by preserving small communication. So just to remind you, now both the prover and the verifier holds k instances, and the prover wishes to convince the verifier it knows the pre-image to each one of them. Our protocol is as follows. The prover samples now k random elements, R1 to Rk, but instead of sending each message separately, it is going to send the product of f on Ri. The verifier now samples k random elements, beta 1 to beta k, and the prover responds with the sum over Ri plus beta I times Wi, which is again, instead of sending each of them separately. We denote those messages as alpha, beta, gamma, and the verifier accepts if and only if f on gamma equals alpha times the product of xi to the beta I. Now, the prover to verifier communication is two group elements which are the same as the original sigma protocol. The verifier here indeed sends k group elements, but it is less significant since when you apply the Fiat-Shamir transformation, it is replaced by applying a hash function, and you can think of a version where the verifier sends a seed for the prover to apply a random marker in order to decrease the communication of the protocol. So now that we have our batch protocol, we are ready to derive the ROG instance bound for our batch protocol. We said that the distribution is hard if given an instance sample from a distribution, it's hard to extract the corresponding witness. Therefore, in order to derive a ROG soundness bound, we are going to construct an extractor that given as input an honestly generated instance x1, which is sampled from the hard distribution, and then it is going to simulate the ROG instance game and specifically the malicious prover itself in order to extract the witness W1. So now we are going to focus on constructing such an extractor. The first trivial extractor uses the +1 special soundness, which is a generalization of the special soundness property. The +1 special soundness property means that given k+1 accepting transcripts, one can extract k witnesses. So our extractor can simulate the ROG instance game many times in order to obtain k+1 accepting transcripts, and then using the +1 special soundness property, it can extract all corresponding witnesses, and specifically to extract W1. However, this solution is very costly, since in order to obtain k+1 accepting transcripts, the running time of our extractor increases while its success probability decreases. And in fact, we are only interested in extracting a single witness, the witness W1. So in order to overcome this issue, we defined a new notion, which we called local special soundness, which means that if you fix an index I star and you wish to find a witness Wi star, given two designed accepting transcripts with a common first message alpha, common challenges beta 1 to beta k, except the challenge beta I star, which has to be different, one can extract the witness Wi star. we show that our batch protocol has local special soundness, and therefore it suffices to construct an extractor that outputs 2 accepting transcripts instead of k plus 1 accepting transcripts. So our extractor is as follows. We simulate the rogue instance game once, and if the verifier rejects, we abort. Otherwise, we simulate the rogue instance game 1 over square root epsilon times with distinct beta I star, and if we indeed obtain 2 accepting transcripts, we can extract the witness wi star using the local special soundness property. Once you have the local special soundness property, it is not very hard to come up with such an extractor. However, its analysis is quite challenging. We show that the expected running time of our extractor is bounded by 2t, and that the second moment of its expected running time behaves similarly the same and bounded by 4t squared. Then we show that the success probability of our extractor is at least epsilon to the power of 3/2, and combined with the second moment assumption, it allows us to derive our rogue soundness bound. So to sum up, we gave a new notion of knowledge soundness for batch protocols, which we called rogue instance soundness. We showed how to efficiently construct batch signal protocols that satisfies this soundness notion. Then I told you that in order to give evidence to support the hardness of the second moment assumption, we showed that it holds for the discrete log in the generic group model. But in fact, we showed more general statement. We presented a framework for analyzing expected time hardness in generic models, such as the generic group model, the random oracle, and so on. And when we apply our framework on the discrete log problem, we get the second moment assumption. That's it. Thank you very much.
Questions? Okay, then let's thank the speaker again. So this concludes this session, and see you back at 3:25.
Hello. Another quick announcement. So we will open the